Okay, so we're going to talk in this video about using ease to do multidimensional optimization. Okay, so we've talked previously about using ease to optimize with a single independent variable. Here we're going to extend that to problems that have more than one independent variable, and therefore they require multiple independent variables to be varied at one time in order to identify the optimal solution. Alright, so we're going to do this in the context of this objective function here. So this is a function of x and y, and the objective function is f. And I'm going to go ahead and enter this into ease. It's a pretty easy function to enter. And then just so I can visualize what's going on, I'm going to make a surface plot and a contour plot of it. So I'll make a parametric table. I'll include in the table x and y, which are my two independent variables, and then f, which is my dependent objective function. I'm going to have 51 values of x and 51 values of y. So I'm going to have a nice, very refined grid to make a 3D plot. So 51 times 51 is, I guess, 2,601 rows. Then I'm going to go ahead and vary x from 0 to 1. So our parameter space for both of the independent variables will be from 0 to 1. And I'm going to do this in sort of repeated patterns of 51. So that's what I've done here. And then I'll do the same thing for y, but I'll do it sort of in the opposite way, where I'll have 51 zeros and then 51 to the next increment and so on. And so that gives me this nice grid. And I'll run the parametric table, which takes a little bit of time. And now I can go ahead and make a 3D plot. So to make a 3D plot, I'll go to plots and then x, y, z plots. And I'm going to just make a surface plot. So that's what I'm doing here. And it takes some time to do the interpolations that are required. But at the end, you get this nice surface plot that you can spin around, and you can get a feel for the objective function. And this is only possible because it's a 2D problem, right? So I can visualize it in a third dimension. The methods we're going to talk about are good for multi-dimensional problems that can extend way beyond just two independent variables. But you can see in this particular problem, there's a kind of lower local optimal that's nice and broad, and it's going to be where a lot of these optimization routines sort of are attracted to. But then there's a global optimal that sits off to the side that's kind of a peak, and it's going to be challenging for a lot of these algorithms to find that peak. And so this is a nice sort of test case to look at. Here's the same surface but shown in contour plots. So I made this using the contour plot with bands, not bands, line selection. But this is a nice way to visualize sort of what's going on. Alright, so because I haven't specified either x or y, I have 2 degrees of freedom, so I can go ahead and select min-max from the calculate menu, and you can see that it brings up this find minimum or maximum dialog. And in this case, because there's 2 degrees of freedom, it's asking me to specify 2 independent variables over here. So I'm going to set this up to maximize f by varying x and y. And just like before, I have to set up the bounds for the problem. So that's basically specifying the parameter space inside of which we're going to explore. So I'm going to specify that x can go from 0 to 1, and y can go from 0 to 1. So it's the same bounds that I've used here for my plot. And a guess value is required by a lot of these techniques, so I'll specify 0.7, 0.7. And then there's these methods that I get to choose from, right? There's the stopping criteria, which I'm going to leave alone here. And then there's these methods. And because I have the professional version of these, there's 5 methods shown. If you have the commercial version, you'll have fewer than that. But let's just go through these one at a time. And just like when we were talking about the 1D optimization algorithms, it's not necessary that you understand these methods, but it is, I think, first of all, interesting. It's really cool, but also useful in the sense that if you have some idea what's going on behind the scenes, you can sometimes select the right method for the problem that you have. So the top method is the conjugate directions method. The conjugate directions method of all of these is probably the easiest to understand, as it basically uses a series of sort of one-dimensional searches to locate the optimal. So you could think about this as E is holding all but one of the optimization variables or the independent parameters constant, and then varying that single remaining parameter in order to locate the optimal value along a line. So see here, maybe if I start here at point 1, which is our guess value, which is where it'll start, it's going to travel along this path 1 in which it holds x constant but varies y, and it's going to locate then the optimal value or the peak of the path there, which is, I guess, point 2. So it can do that using any of the one-dimensional optimization algorithms we talked about before. Once it gets to point 2, now it's going to hold the other another independent parameter constant. So in this case, it'll hold y constant and vary x. So it's traveling along path 2, and it locates point 3. And then because there's only 2 independent parameters, it goes back to the first one and starts over again. So now it'll move along path 3 and basically not move, because it'll find that it's already at the top, and it'll be done here pretty quickly. This isn't quite right in the sense that the paths, the 1D paths that it takes are not necessarily lines of constant independent parameters. Instead, it's using conjugate directions, but the basic idea is right here. And you can see that this is a technique that's going to start at a guess value that you provide, and it's likely to miss a global optimal and rather find a local maximum. So if we go ahead and use this technique, so I'll just select it and hit OK. Yeah, you can see the results here. It took a few iterations, and yeah, it did not find this local global peak. Instead, it sort of settled on the smaller local optimal at 0.5. All right, so that's the conjugate directions method. The next one is the variable metric method, and this one is an awful lot like the quadratic approximations method for 1D searches, which we talked about previously, where basically the method samples the parameter space, and using the points that it finds, it fits a quadratic. So for a 1D search, it would fit a quadratic in 1 dimension. For multiple dimensions, it's going to fit a quadratic that has multiple independent parameters, but it's basically the same idea, where it's going to then use this quadratic approximation to the surface in order to estimate where the optimal value is, go there, and then do the whole thing again. Right. So again, because it's going to start at the point you said that it should start at, so the guess value, it's likely to not find a global optimal, but rather sort of be attracted to a local optimal. So here I'll go ahead and use this technique, and you can see it's about the same in terms of efficiency as the conjugate directions, but it actually was able to find the global optimal, whereas the other one did not. Alright, so let's move on to the next one. So the next one is one that's called the Nelder-Mead Simplex method. It's only available with the professional license of ease. But basically you can think of this as using what are called simplexes. So this is basically n plus 1 test points at a time. So n being the dimension of the problem. So for our 2-dimensional problem, n is 3. Which means that our simplexes are simply triangles, right? They have 3 points, they're triangles. And the method, every iteration, adjusts the triangle by moving or throwing away one of the points in an intelligent way, right? So here you can see kind of a sequence showing how the simplex, our triangle for this problem, is moving around trying to crawl up that hill in an intelligent way. And it's pretty easy to To implement it again, you just have to select it and hit go, and you can find that it does find again the local optimal, not the global optimal, based on where it started building triangles, and that it took more iterations to do that. Alright, so let's move on to a couple that are maybe a little more powerful. The direct algorithm is one that takes the entire parameter space and basically calls that a region and samples the entire parameter space using a regular grid, and then it looks at each point, and based on where it finds local maximums, it forms smaller regions around those, and again samples those smaller regions using a regular grid, and very slowly it will converge, usually more reliably, to a global optimal because it is sampling the entire region. So here's just a sequence showing how this might work for this problem, where you start with a region that is the entire parameter space, and then you end up looking at smaller and smaller regions, and eventually you actually converge to the global optimal for this particular case. If I go ahead and run this one, you can see that it requires even more iterations than the other ones, but it did get to the global optimal. And that leads us to the genetic method. This is again only available in the professional version of ease, but this one is it's designed to reliably locate global optimals, even in a surface that has a lot of local peaks. And the idea here is that the genetic algorithm will mimic the processes associated with biological evolution. So you start with a population of individuals, which are just sample points that are chosen semi at random across the entire parameter space, defined by your bounds on your independent variables. These individuals then are sampled to determine their fitness, which is simply the value of the objective function, and then the next generation is generated by breeding the selected members of the current population, and their likelihood to breed is based on their fitness. So ones that have a higher value of objective function are more likely to pass on their genes to the next generation than ones that are at lower values of the objective function. And then you inject into this a mutation rate, and basically you have something that looks a lot like biological evolution. And you can, when you select this, you see you get these sliders where you can adjust the number of individuals and the number of generations and the mutation rate if you'd like. Once you settle on something here, you can go ahead and run it. And here I've just shown what successive generations look like. And so you can see kind of an initially dispersed population that quickly finds the local optimal, but then because of the mutations, it'll go ahead and eventually attract the population over to this global optimal. And if we run this, you can see that first of all, it does take kind of a long time because it's simulating many individuals, but it does eventually find the global optimal. But this is thousands of iterations now, so it is kind of a brute force method relative to the other ones. So those are the different multidimensional optimization techniques you have, and the optimization capability is really powerful. Both for engineering design, where you are literally trying to choose the best values of independent parameters, but also for other things like curve fitting, or sometimes if you have a very difficult set of equations that won't converge very easily, you can set it up as an optimization process and get a solution that way. Sometimes you'll have constrained optimizations, which is a whole other sort of topic that we can cover in a different video.